Okay, so we're on the next part of section 4.5 and we're continuing our hunt for asymptotes. Last time we saw that when we look at the degree of the polynomial function in the numerator and compare it to the degree of the polynomial function in the denominator, we'll let n be the numerator, m be the denominator degrees. We looked at when it was less than, or when they were equal, you wound up with a horizontal asymptote. So it would be some sort of a horizontal line. What we want to look at now is this. What's missing here is what happens when n is greater than m. When n is greater than m, there is no horizontal asymptote. However, there is an oblique or a nonlinear asymptote. And basically what that means is a line that's on an angle. That would be oblique. Think about y equals mx plus b, where you have a line with a slope. So we can have sloped lines for asymptotes, or if it's nonlinear, now we're looking at curves. So you could possibly have like a parabola as an asymptote. Okay, but whether it's oblique or nonlinear, you have to have an equation, okay? Whereas up here for horizontal, or even when we looked at vertical asymptotes, you just get a number. And that's where that line goes through the axis. For these guys, we're going to need an equation. So how do we get that? Well, it's pretty easy. What you do is you take the denominator and you divide it into the numerator, and we were calling that p of x. When you do that division, you'll get a quotient. The quotient is the equation of the non-horizontal asymptote. So that's all you got to do. Now, let me get this. Okay, two things. Number one, if you think back, if the degree here is greater than 1, so like you had x squared, 3x cubed, that kind of thing, you have to use long division like I have it set up. However, remember, if this is linear, d of x, then you can use synthetic division, which is a lot easier. So the synthetic division is available for linear denominators, so we say. Okay, what else? With the horizontal asymptote, the curve may or may not cross, and we had a way to figure that out. For this one, it's a little bit different, probably easier. When you do the synthetic division, or you do this, you're going to wind up with either 0 or a remainder. Sometimes a remainder will be in another equation. So you find the roots of that equation. If there are roots, that's where the graph will cross this asymptote. So do the division to get the equation of the asymptote, and then to find out if the graph is going to cross that asymptote or not, what you're looking at is zeros of the remainder. That's where you cross Okay. All right, so let's try one. Yeah, what do we got here? 9 minus x squared over x minus 1. And let's kind of go through some of the other stuff we've done, and we'll try and do a little more on this graph than just put in the asymptotes. Okay, we learned earlier zeros of the denominator will lead to vertical asymptotes, and in this case, if x equals 1, we get, this is solved, so that's a 0. So at x equals 1, we have a vertical asymptote. Let's go ahead and put that in there. That would be right here. X equals 1. Okay, so there's our asymptote. Okay, and then we wanted to check for vertical asymptote. So the degree up here is 2. We want to compare that to degree of the denominator, which is 1. Well, here it is. N is greater than m in this case. That means we're going to have a asymptote here that's not a horizontal line. Okay, so again, it's a normal division problem, just like you would think of this. It's this divided by this. This is linear, has a degree of 1, so synthetic division is available. So again, with synthetic division, I put in the 0 of this, which would be 1. If x was 1, that's the 0. I put in the coefficients here, and 0 fill the missing ones. So x squared is a minus 1. X is missing, so I got to put a 0. And then I got 9 for the constant term. Draw the line, bring it down. Minus 1 times 1, add them up. Minus 1 times 1, add them up. I got a remainder of 8. And again, recall that if I'm dividing an x squared by an x, this is going to reduce by 1. So that's actually an x, represents a coefficient on x. So what do I have here? Minus x minus 1, remainder 8. That's the equation of the in this case, oblique asymptote. If it was a squared or a cubed or something, then it's going to be a nonlinear, and you're going to have a curved asymptote. But this is the equation actually of a straight line if you look at it. This is y equals mx plus b. Where what? The slope is minus 1. That means it's a downhill line. And the y-intercept is at minus 1. So if I go to my graph here and I go to minus 1, and then I have a slope of minus 1, so that means I'm going to go up 1 to the left 1 or down 1 to the right 1. I got to make it negative. So it's going to go like this, and so on. So I can sketch that. So here's my asymptote. Looks kind of like that. Okay. Will it cross the asymptote? No, because if you look at this, you got to have an equation here so that you can solve for roots. So the idea of a root is, when can this equal 0? When can 8 equal 0? Never, right? So that means you'll never have a solution or a root there. It means the graph will never cross this asymptote right here. Okay, so that's this piece. Now we're ready to start graphing, but we're going to do graphing more formally in the next section, but let's kind of start now with what we need are some points so that we can kind of sketch the graph in. So something we always use is the Y-intercept, and that's something that's easy to compute and something you really need when you're trying to sketch a graph. So what does a Y-intercept means? That means x is 0, right? Because if I'm crossing the y-axis, I'm at 0 on the x-axis. So all you do is you evaluate the function at x equals 0 and see what you get. This is just going to be -9. So I'm going to cross the y-axis at -9. So I can go ahead and put that point in there. So I know I'm going through there somehow. Some other handy points, if they're available, are X-intercepts. Now for X-intercepts, that means y is 0. So if I say I'm crossing the x-axis here, the value on the y-axis is 0. So that means the function has to be 0, but the only way for this function to be 0 is if the numerator is 0. So for X-intercepts with rational expressions, what you're looking for are zeros of, we'll call it p of x in the actual definition, but it's zeros of the numerator. So all we got to do is find those. Now the other thing is we got to make sure that any of these zeros here are not also included down here because these are out of the domain. So in other words, if one of these zeros equaled 1, we'd have to throw it out. Okay, but it's not going to be the case here. Let's see. So if I take the numerator and I set it equal to 0, solve for x. All right, this is the difference of two squares. So my zeros are 3 and -3. So in other words, these values, they're not excluded. Only x equals 1 would be excluded from the domain. And each of these values makes that equal 0, which would make the entire fraction equal 0, which would make y, or the function, equal 0. So when y is 0, x can be -3 or 3. Okay. So I actually probably got enough here to graph it. If I'm not sure, I could just pick extra points and plug them in and see what y values I get if I wanted to find more points. But I think for now I've got enough to make a decent sketch. Remember, these are asymptotes. I'm not crossing asymptotes, so I'm going through this point here and this point here. When I go through here, I'm going to start getting close to this line, but I'll never touch it. And then I just got to kind of try and connect this up and then start off towards that asymptote. And then over here, the same thing. I got to go through this line, or this point, and I got to go up, but I can never touch the asymptote. So a little ragged looking, but that's how it is. Now, how do I know I go through these? Well, I mean, it makes sense looking at it, but one other thing that we didn't really stress here, but we looked at it last time. Remember, the multiplicity on these zeros is 1. When you have an odd multiplicity and it equals 1, then that means you go through that 0. remember, if these would have been even, you would bounce. And then if they start getting bigger than 1, you flatten out as you go through or bounce. So we're guaranteed that we go through the points just by looking at the multiplicity here. Okay, so that's a good example. What we're going to do on the last part, I'm going to graph a couple from the start, and we're going to do the entire graph kind of like this, but they're going to be a little more interesting. And we're going to kind of base it on some guidelines that you might want to look at. And they're on page 395. And it's basically kind of what we just went through here, but it's a kind of a nice table on all of the different things you should collect and put onto a graph so that you can sketch a reasonable picture of what the graph would look like.